So the first step, k multiplications. All right, yeah. So here I need to erase, yeah. Okay, yeah. The strategy here, do experiments. 1, 2, conclusion, k. Okay, all right. Now, the question, is your algorithm efficient? Because the goal is efficiency. Yeah. But when we use k multiplication to calculate this term, we do not see any problem, right? Yeah. It's normal. Everything looks normal. Yeah. Nothing is wrong here. Yeah. But because our goal, we want to find the fastest way to calculate. Yeah. Question? Yeah. We want to find some fastest way, to calculate the polynomial. Yeah. But here, because the polynomial is relatively complicated, let's just consider the fastest way to calculate one term. Here, is this the k multiplication way the fastest? Is it possible we can reduce this k number? That's the question. Okay? Yeah. Is it possible we can find a smart way to use fewer multiplications than k to find this, single term? That's the question. Okay? Yeah. All right. Find the performance number of this algorithm. Yeah. So here, but there is another question. Yeah. So another question, because we want to study the efficiency of algorithm. Here, another thing is, because when we use the word efficient, then we need to define some measure for efficiency. Right? We need some measure for efficiency. Okay. How do you measure efficiency? Right? That question. Okay. So here, the measure is some performance number. Yeah. We need some quantity to represent the efficiency. Yeah. All right. And subjective to objective. Yeah, because when you talk about some algorithm efficient or not, when you say one algorithm is efficient, for different people, their efficiency description could be different, right? Yeah. So one person may feel this algorithm is efficient, but if you change to a different person, then that person may feel it's not efficient. Okay. So for that reason, so we want to make our efficiency measure objective. Okay? Yeah. So then we have a number. Everyone uses the same efficiency number. Then we can compare, right? We can compare the efficiencies. Yeah. All right. Yeah. But so this topic we will elaborate later. Yeah. All right. Now the question: are we satisfied with this solution? Yeah. Is it possible we can do slightly better than this current answer? Yeah. That's another question. Yeah. Here we do not know how bad it is. Yeah. Because that's the only way we know to calculate this term, right? That's the only way. If you have a different way, then you can compare. Okay? Which way is better? But if you only know one way, how do you know this way is good or bad, right? Yeah. If that's the only way we can do, then because we do not have reference, we do not have comparison, reference, so we do not know if it's a good way or bad way. Yeah. So we want to, so at least the first thing we want to figure out, we want to see if we can find a different way to calculate this term. If we can find a different way, then we know we can do comparison. Yeah. All right. Consider the simplest case, x to the k. So here, let's ignore that coefficient. Yeah. AK coefficient. Yeah. Because that's one multiplication, right? Yeah. So let's simplify the general term. We only consider this monomial, x to the kth. Yeah. Monomial. Here, yeah, this x to the kth, yeah, the general monomial, yeah. But how about let's consider a special monomial here. Yeah. Here, let's look at the special monomial. X to the fourth, this is a special monomial. The question, all right, if we use our old way, this old way to calculate, yeah, or this old way to calculate, yeah, because our AK becomes 1, right? When we calculate x to the fourth, AK becomes, coefficient becomes 1. So we can save one multiplication, right? Yeah. We can save, because we do not need to do that. A4 times x to the fourth. We do not need to do that multiplication. So we can save one multiplication. Then you need 3 multiplications, right? Yeah? Because based on the way we do, we do not need 4. We can save 1. Okay, that's why here, if you use that old way, you need 3 multiplications. The question is, can you do better than 3 multiplications? Here we want to see if we can do better than 3 multiplications. So let's try. The first multiplication, ax times x equals x squared. That's 1 multiplication. Yeah. All right. Then we need to find x to the fourth. So the second multiplication, because we already have x squared, right? Yeah. So we already have this x squared value. Can we use this x squared value twice? X squared times x squared. So we get x to the fourth. So we do not need to calculate x to the third, right? Yeah. Why we need to go through x to the third? After we get x squared, can we find x to the fourth directly from x squared without calculating x cubed? No. Yes. We can save 1 multiplication here. So if you do multiplication in this way, you only need 2 multiplications. Right? So better than that's 3. Yeah. So that's why for this example, you know, we can do better. Actually, we can do better than the common way here. Okay? Yeah. Because most people use this way, right? Most people use that way. Okay. So here you can see we can do better if we can discover some smart way. We can do better. Yeah. So here, although we reduce from 3 multiplication to 2, 1 multiplication reduction, but it's a good sign. Okay? This gives us some good sign for improvement. All right, yeah? So we are encouraged. Yeah. From that simple example, we are encouraged. So we know actually we can do better. All right. Yeah. So now we want to find that smart algorithm. Yeah. All right. So let's continue our analysis. Yeah. All right. Yeah. So here, now we want to, really find that smart way. Yeah. All right. And currently we have that brute force method. Yeah. So the brute force method. Yeah. So we know that method can be improved. Yeah. But the brute force method, that's our starting point. Yeah. We know it's not the best way. It's our starting point. Yeah. So the first we want to do the counting. Count the number of additions and the number of multiplications in this brute force method. If we apply the brute force method, how many additions do we need? If we apply the brute force method, how many multiplications we need? Yeah. That question we want to answer. Okay? Yeah. Now after that, then we do improvement. We want to see how much we can improve our algorithm. Yeah. All right. Yeah. So here we need to do the counting. Yeah. Counting. Yeah. And when we do the counting, so here you can see we apply additions and multiplications in certain order. Yeah. In certain order. In the natural order. Yeah. Yeah. So you know the rule for the order, right? Yeah. So we learn, the general rule. Yeah. The order of the operations to apply when we calculate this expression. Yeah. All right. All right. The question. Although that order is the general order, most people use that order, but the question is, can we change that order? Do we have different orders to use for the same polynomial? That's another question. Yeah. Another question. Yeah. So this question is a little deep. Because it's not easy to see which order to take the operations, additions, multiplications. Yeah. All right. So we need more information regarding the orders of the operations. Yeah. All right. Next. Yeah. Then we come back to the, remember, efficiency measurement, that question. So here, let's answer the efficiency measurement. How to measure the efficiency? So this question, can we use the execution time to measure the efficiency? And most people like to use the execution time to measure the efficiency, right? Yeah. The shorter the execution time, the better the efficiency. Like that. But there is some problem. Yeah. Although this is the straightforward measure of the efficiency, but there is some serious problem if you use this measure. Yeah. The serious problem is this measure is unstable. Execution time is unstable. So what do you mean unstable? Yeah. Because execution time, when you clock it, you need to run your program in certain machine, right? Certain computer, certain machine. Yeah. But which computer do you use? Okay, which machine? Yeah. So the hardware, the computing power of the hardware is important, right? Yeah. So you can use a supercomputer, yeah. Supercomputer, PC. If you're a PC or supercomputer, the execution time will be different. Yeah. So for that reason, so we treat this execution time measure is unstable, because you cannot specify what type of machine to use. No. All right. Unstable. Different machines, so from the hardware perspective, it's unstable. Yeah. Another, from the software perspective, so when you write programs, even you use the same hardware, yeah, but different programmers, they implement the algorithms differently, right? Yeah. Experienced programmers, beginner programmers, although they implement the same algorithm, but the result could be different. Yeah. So experienced programmers, they know how to make the program running faster. Yeah. How to manage the resource efficiently to make the program run faster. Yeah. But beginner programmers, they do not have a lot of experience, so their program implementation, so usually slower. Yeah. So even from the software point of view, this measure also unstable. Execution time measure unstable. Yeah. So we want to find a stable measure. Yeah. So the stable measures does not rely on hardware and software. Okay? Nothing to do with hardware, software. So always the same number. Yeah. Then that's a stable, yeah, objective, stable measure. Yeah. All right. So how to measure efficiency in a stable way? Okay. Yeah. Here, the best way, so we use the number of additions and number of multiplications. We count those numbers. Number of additions, number of multiplications. So you have concrete numbers, right? Yeah. Then, it does not rely on your hardware, right? If you use supercomputer or you use simple PC, low-end PC, you need to use the same number of additions, right? Same number of multiplications. Yeah. When you write a program in some efficient way, some inefficient way, you need to do the same number of additions and multiplications. So this way, you will get objective and stable efficiency measure. Okay, so that's the much better measure than the execution time. Yeah. All right. So after we understand this concept, okay, efficiency measurement concept. Yeah. Now, yeah. Next, we need to do the counting. Yeah. But when we do the counting, there is another subtle question we need to consider. So, because here we have two operations, addition operations and a multiplication operation. But these two operations are quite different. Yeah. The CPU time used for addition and multiplication quite different. The difference is pretty big. Here I'm talking about CPU time. Okay. We know inside CPU the time used, execution time used for addition, very fast, extremely fast. Yeah. For multiplication, also very fast. Yeah. All right? Yeah. But they are different. The execution time for these two operations on the same CPU, quite different. Yeah. So we need to consider that difference. Yeah. All right? Yeah. So how different? See here, how different? We need to know how different. Yeah. Yeah. So here, in order to do fair comparison, right? Yeah. Because in this algorithm, we need to use both additions and both multiplications. Now, we want to use some fair measure to incorporate both additions and multiplications. And because if we compare addition and multiplication, it's like, apple and pear, two different objects, right? Addition, multiplication, two different objects. Yeah. So when you compare two different objects, you have some problem, okay? Yeah. So here we need to, try to find a fair way to measure additions, multiplications using some unified way. Okay? Yeah. Otherwise, it's not easy to compare. Yeah. For example, you have 100 additions here, you have 200 multiplications there. Then another algorithm, you have 300 additions here, but you have 50 multiplications there. Which one better, right? You don't know which one better, okay? Yeah. So two different algorithms. So that's why you need to, bridge these two objects. These two objects, there is some big difference between them. So now we need to establish some bridge between these two objects. Okay? Then you can compare in a fair way. Okay? Yeah. So that way, these two different ways, we can compare in a fair way. So that's what we need to do here. Yeah. So for that reason, we add assumptions. Yeah. So what's the assumptions? To bridge the gap. Yeah. Each addition, we know addition is faster than multiplication, right? In CPU. Yeah. So it's very easy to know. In CPU, addition is faster than multiplication. Yeah. Yeah. So how much faster? Yeah. So we set. So each addition takes 1 unit of time. 1 unit of time. Okay? Yeah. Yeah. All right. Each multiplications take 10 units of time. So multiplication needs approximately 10 times of the execution time of that of the addition. Yeah. So this comes from the the CPU architecture. Yeah. If we go back to the CPU architecture, the ratio is 10-to-1 ratio, approximately. Yeah. So that's the real world situation, 10-to-1 ratio, approximately. Yeah. Then in our assumption, we assume each multiplication takes 10 units of time. In that way, we can use the number of time units. That's do comparison. Then we have a unified way, right? No matter you have how many additions and how many multiplications, you can calculate the number of time units you need. Then you compare the number of time units between two different algorithms. That's the idea. Okay, all right. So let's move to the next topic, B.2, estimate the cost. Now we can estimate computation cost. Subproblem 1. Let us count the number of additions. Yeah. So that's our brute force, straightforward, direct way. When you do the calculation of this polynomial, how many additions do you need? Can you see it? Yeah, here. Another question. Yeah. Our subproblem 1. We need to count the number of additions. Yeah. Can you see that? Yeah. Yeah. Another problem-solving question we need to answer. Yeah. So here, if you cannot see immediately, yeah, because here, there's the problem here. So why you cannot see the answer immediately? Because in our representation, you have this dot, dot, dot thing. So we skip many terms. When you use the symbol dot, dot, dot to skip many terms, you have the problem to keep track of the data. Remember? Keep track of the data. So here, we need to find a way to keep track of the data, so we won't get lost when we count the number of plus signs. So here, in order to count the number of additions, because we know each plus sign corresponds to one addition, right? Another plus sign corresponds to another addition, and so on. Okay? Yeah. So the question, how many plus signs do you have in this P formula? P of X formula. Because there are many skip it terms, so you get lost. You cannot keep track of your data. You cannot keep track of all the plus signs, right? Yeah. So you need to find a way to overcome. Yeah, Mitchell, yeah, one student, plus n plus 1 additions. Yeah, one student told me n plus 1. Yeah, all right. I want to say it is very close, but if it is correct or not, then we need to really find a solid way, okay? Yeah, to give us the answer. All right. Here I want to introduce a counting technique, a basic counting technique here. All right. All right. So the strategy we want to do here, we work on easier parts first. Yeah. All right. Yeah. Yeah. So here, this dot expression. Yeah. So we want to overcome this problem. Okay. Keep track of all the plus signs. Yeah. All right. So how finally we keep track of those invisible terms? There are many invisible terms. But how do we find a well-organized way to keep track of those invisible terms? That's the technical question we need to solve. Okay, yeah. All right, so here we use a counting technique, some effective counting technique here. We call it counting by reference. So we need to find appropriate reference. Then we do the counting. Yeah. All right. So the key point, what reference objects? So reference means reference objects. What reference objects do you want to use here? Yeah. So the essence of this methods, we want to discover one-to-one correspondence between two mathematical objects. When we do the counting, so what do we count? Mathematical objects. Our first mathematical objects, our target, the plus sign, right? Each plus sign That's our first mathematical object, plus sign. Okay? But the plus sign, hard to count, relatively hard to count. Now, we want to associate each plus sign to another mathematical object, different mathematical object. But that different objects can be counted easily. That's the idea. Okay, all right. Here, I use a simple diagram to explain this idea, counting by reference idea. There are two different objects. Okay, and we want to find one-to-one correspondence between these two objects. Yeah. Object 1, hard to count. Yeah. The plus sign, hard to count. Yeah. But object 2, easier to count. Then, because since their relationship is one-to-one correspondence, then the number of object 1 should be equal to the number of object 2, right? Yeah, one-to-one correspondence. Same number. But when you count number of object 2, it is much easier, so you can count easily. Then you can use that counting number to, for the object 1, for the counting number of object 1. Yeah, that's the basic idea. Yeah. So let's apply the idea in our current question here. Yeah, and see if it's n plus 1. All right. Object 1 plus sign. Okay. Yeah. So what is object 2? That's important. Object 2. What's that object 2? Okay. All right. Object 2, a subscript. Okay. So for example, the first plus sign we associate with the first, A1, the subscript of A1 coefficient. Okay. The second plus sign we associate with A2 subscript, and so on. And the last plus sign we associate with the A sub n subscript. Okay? Is it one-to-one correspondent? 1 plus sign corresponds to one of the subscripts of our coefficients. Yeah, yeah. But no correspondence for A0. No plus sign corresponds to subscript of A0 coefficient. Yeah. All right. Yeah. So then, next, now you can see, yeah, in this way, one-to-one correspond. Is it easy to count? Is it easy to count these subscripts? Yeah. So here, let me list the subscripts. The first plus sign corresponds to 1. Second subscript corresponds to consecutive integers, although ... but we know they are consecutive integers. Consecutive, last one is n. How many integers in this list? We count object 2, number of object 2. That's easy. The number of consecutive integers in the list, how many? Starting from 1 through n, consecutive. Yeah. It's very easy to keep track of all the numbers in the list, right? Because consecutive. Very easy to keep track of them. Yeah. So there are, the number is n numbers in the list, right? Yeah. So then you can go back, you can make your conclusion. You have n plus signs. That means you have n additions, yeah. Not n plus 1. Yeah. Not n plus 1, okay? Yeah. But very close. Yeah. Here, we need to use this counting by reference technique. You need to find the appropriate reference. Yeah. Yeah. Right. What happened A0? Because here, yeah, A0. So think about that. Yeah. A0. Because we do not need, you can put a plus sign in front of A0, but this is unnecessary, right? Yeah. Even if you put a plus sign in front of A0, but that addition is unnecessary. So you can save that, right? You do not have to do that. Yeah. Okay? If you really want to, include A0, you may 0 plus A0. Okay? You add 0 plus A0. But this is unnecessary. That's why you do not include A0. You can save one addition. Okay? You can save one addition. Yeah? So you do not include A0. Okay? Yeah. All right. Yeah. So when you do your work, you need to pay attention to the little things. Yeah. When you do the one-to-one correspondence, your first plus sign, you map it to the first subscript right after this plus sign. Right after. Okay? Yeah? Not before this plus sign. After this plus sign. But right after. Okay? The second plus sign, the subscript right after the second plus sign. And so on. Okay? Yeah. The last one, the subscript right after that plus sign. Yeah. You need to maintain that order. Do not mess up. Okay? Some places you use subscript before the plus sign. Some places you use the subscript after that you mess up. Okay? You should make the one-to-one mapping correspondence consistent. Okay? Consistent. Yeah. Follow the same rule. Follow the same rule. Yeah. Yeah. So that's the way we organize our data. Okay? Yeah. Try to feel about it. Okay? So this method. Yeah. All right. Let's move to next subproblem. The first subproblem, our answer is n. Yeah. N units of time. Okay? When we calculate additions, we need n units of time. All right. Now let's move to the second subproblem. This time we need to count the number of multiplications in the brute force method. Okay, all right. Yeah, so the typical term, let's recall, we need k multiplications, right? Yeah. Now we need to accumulate the number of multiplications for all the terms. Yeah. Yeah. All right. All the term here we have n plus 1 terms. Yeah. Although n plus 1 term, but the first term A0 we don't need a multiplication, right? A0 term no multiplication. Yeah. Then A1 x term 1 multiplication and so on. Okay. All right. So here let me list the number of multiplications for each term. Yeah, yeah. So 1, yeah, 1, 2, 3, the last one, n multiplications. The total, so we do the summation from these n consecutive integers from 1 through n, and we know the formula 1/2 times n plus 1. Consecutive integers. Yeah. All right. Yeah, that's the number of multiplications. Yeah. But remember here, we are counting the number of multiplications, but we need to convert, some unified measure. So we need to use the time units. We need to calculate the total units of time for the multiplication. Yeah. How much is that? Okay. Yeah. All right. N additions corresponds to n units of time. Yeah. Now here, this many multiplications, we know each multiplication has 10 units, right? Yeah. Based on our assumption, each multiplication has 10 times units. That means we need to multiply this number by 10. Okay? Yeah, 10 over 2, 5. So the units number is 5n times n minus 1 units for the multiplication part. Okay? Yeah. So we multiply the number multiplication formula by 10 to get a unit number. All right. Then the total units number, addition part contribution and multiplication contribution 5n times n plus 1. So adding together, so the total unit number 5n squared plus 6n. Okay, that's the total unit number. All right, yeah. For our brute force method, we know it's not the best one. Definitely we can improve it. But this is our starting point. So when we try to find a better algorithm, because we need to compare with this first try. This is first try. Yeah. All right. Yeah. Now we need to move to the next question. How to reduce this number? Yeah. All right. Improvement strategy. All right. All right. There are two parts to be improved on. Well, so addition part, multiplication part. Okay? Yeah. So the question, which part is more important? So when you have limited resource, so here let me describe the situation. Suppose you have the limited resource. Y is n minus 5n. And what's your question? Yeah. Y it is. Yeah. So if I 5, yeah, go back. Yeah. So here. Yeah, here. Which one? Yeah. What's your question? Michelle, your question? Total units and all right, yeah. So number multiplication n times n plus 1. All right, yeah. But in order to convert it to the number of units, you need to multiply by 10. So that's why 1/2 times 10, you get a 5. Okay, yeah. So n plus 5n times n plus 1. All right, yeah, yeah. Yeah, all right, yeah. So yeah, so you when you go back, you can try to follow the formula closely, yeah, on your scratch paper. Yeah. All right, yeah. Let me keep going. Yeah. So regarding the improvement, there are two parts. So which part should we focus on? Yeah. If you have limited resource, then you need to put your resource in the most important part. Okay? Yeah. So here, addition part and the multiplication part. Which one you get the best reward? Yeah. Okay? All right. Yeah. So here, observation. Yeah. We know the ratio of these two operations 10-to-1 ratio. Yeah. Unit cost of multiplication over unit cost of addition 10-to-1 ratio. Yeah. All right. Yeah. So which part do we have more room to improve? More room. Okay. All right. We know in this expression, n for addition, okay? N for addition, and the remaining 5n squared plus 5n, that's for multiplication, okay? You see, 5n squared plus much larger than n, okay? All right, so if I draw diagram, so this big circle represent the total number of units, time units, all right, then only a small portion for addition, okay? So this small portion for addition, and all the, the big part, okay, this big part, that's for the multiplication. Now, you want to improve, you want to reduce the total number of units. Yeah. Which part you want to put your limited resource on to reduce? Do you want to reduce the addition part, or do you want to reduce the multiplication part? Yeah. So definitely the multiplication, you have more room for improvement, right? Yeah. Because this, so big. Yeah. The portion for the multiplication is so big. So you have a lot of room for the improvement. Yeah. So here there is a, strategy. Yeah. Another strategy people use in the real world problem solving. Okay. Yeah. So that strategy is focus on the major part, because the multiplication part is the major part. The percentage of the multiplication in the overall execution time, it's much larger than the percentage of the addition part. Yeah. So we should focus. Focus means we put our limited resource on the major part, the multiplication part. Then our gain is much bigger than the opposite way you put your limited resource on the minor addition part, then your gain is very little. Your gain is very little. Okay? Yeah. So that's the main point. Conclusion. Focus more on multiplications. Yeah. Here the strategy. Yeah. So now our strategy based on this principle. Yeah. Here you can treat it as a principle. Based on this principle, so our strategy becomes we want to reduce the number of multiplications. Yeah. All right. Yeah. The new question, how to reduce the multiplications. Yeah. All right. B.3, Horner's rule. Horner's rule. Yeah. So this, well-known, smart way to calculate the polynomial. Yeah. So we can see we can reduce the number of multiplications significantly. Yeah. All right. Yeah. The strategy. Yeah. Now our focus is on the multiplication reduction. But the question, how do you reduce the number of multiplications? Yeah. So we use the strategy. We want to study a simpler case. Yeah. If we work on this formula directly too hard, we have no idea. We don't know how to reduce the number of multiplications. Yeah. Now, in order to make our work easier, so we want to study a simpler case. All right. So what is the simpler case? Yeah. So we choose relatively small n number here. Okay. All right. Do simple experiments. Yeah. All right. Yeah. So we discover certain property from experiments. Yeah. So, all right. So when the data size is small, then it is much easier to manipulate the data. Yeah. All right. Then, so now, let us do our work. Okay, all right. Let's consider n equals 2. Yeah. Not n equals 1. Yeah. N equals 2. So why not n equals 1 is simpler than n equals 2. Yeah. Although it's simpler, but it is too simple. If it's too simple, you have no room for improvement. Okay? Because it is already the simplest form. There is no room for improvement. So that's why we should not work on the n equals 1 case, because there is no room for improvement. But if you do a little larger data size, n equals 2, then at least you have some room for improvement. Yeah. So that's why we consider n equals 2. P sub 2 of x, it is a quadratic polynomial a0 plus a1x plus a2x squared. Okay, yeah, all right. Now let us try to discover some property here. The property in these two terms. So what is the property? Some useful property if you look at these two terms. Yeah. The property is they have common factor. There is a common factor between these two terms. The common factor is x. X is the common factor. So we want to use this common factor to do some manipulation. Yeah. Form change. Yeah. All right, the common factor x. Yeah. Factorization. Yeah. When you see common factor, you know you have room to do factorization, right? Yeah. Factorization operation. Yeah. All right, let's do factorization. a1x plus a2x squared equals, you factor common factor x out. So inside the parenthesis, you have a1 plus a2x. Okay? Yeah? Yeah. So you change the form. The result of this equality, the two sides, result of the two sides the same, but they have different forms, right? Yeah. The forms at two sides are different. So the two different forms would result in different number of multiplications. When you count the number of multiplications from these two different forms, your answers will be different. Yeah. When you count number of multiplication from the left-hand side of the equality, you have 3, right? The first term, 1 multiplication. The second term, 2 multiplications. So 1 plus 2, you have 3. Yeah. But when you count the number of multiplication in the right-hand side, you only have 2 multiplications. Yeah. Because x times the parenthesis, that's 1 multiplication, and a2 times x, another multiplication. You only have 2 multiplications. So the number is different. 3 versus 2. And 2, we get improvement. Yeah. So here you can see, if we do factorization in this way, we can improve the number of multiplications. That's the good side. Yeah. We can improve. Improve. The key to the success of this improvement is because we can do factorization. That's the key to the success. Okay? All right. Yeah. All right. Yeah, so the conclusion. Yeah. If we if we can use this. Oh yeah, so we run out of time. So I set a clock. Yeah, so I won't. Okay, good. Yeah, so I will stop quickly. Yeah. All right. Yeah. The factorization. Yeah. The reason we can improve the number of multiplication, we have gained from 3 to 2 because we apply factorization. Yeah. So we know next, in order to get the best multiplication reduction, we should use factorization as much as we can. Yeah, because that's the main reason we can do better, right? This factorization operation, that's the reason we can do better in multiplication reduction. Okay? All right. So let me stop right here. So the next time I will show you how to apply the factorization to calculate the whole polynomial. All right, yeah. So see you next time. Yeah, but Friday I will give you quiz 1. But I haven't finished part B. Yeah, part B. So we have a lot of materials left. That means you cannot do all the questions in quiz 1. Yeah. So probably you can do half of the questions. Yeah. So you do not have to complete all the questions in quiz 1. Yeah. But after lecture on Monday next week, then because after we finish part B, then you can complete all the questions of quiz 1. Okay? So don't worry, some questions if you cannot understand well, so you need to wait until we finish the lecture on Monday next week. Yeah. All right. Yeah. So see you Monday in the classroom.